With this, I will introduce our first speaker for the day. Our first speaker for the day is Dr. Mahdi Rabbani. Dr. Mahdi is a postdoctoral fellow at the Canadian Institute for Cybersecurity here at the University of New Brunswick. He currently leads two projects, one on detecting the smishing attacks and another on mitigating the credential tweaks attacks, while also contribute to a separate malware analysis. Previous to this, Dr. Mahdi led a project focused on access management system for IoT devices, including IoT device identification and anomaly detection. Prior to this, Dr. Mahdi was a visiting researcher at the Dalhousie University, where he focused on machine learning and deep learning approaches for detecting DDoS attacking in IoT devices. He received a full scholarship for his PhD in computer science and technology at the Nanjing University of Science and Technology in China, where he graduated in the year 2022. His PhD dissertation was titled MLDL Approaches for the Malicious Behavior Detection and Recognition in Intrusion Detection Systems, demonstrates his commitment to advancing the field. Additionally, Dr. Mahdi completed his MTech in Artificial Intelligence at the University of Mysore in India before pursuing his doctoral study. Dr. Mahdi has contributed to the field of cybersecurity with numerous publications in various journals. His research interest includes AI for cybersecurity, malware analysis, graph learning, machine learning, and deep learning-based network anomaly detection and recognition, as well as the privacy enhancing techniques for IoT devices. This was a very short and a brief introduction to Dr. Mahdi. And at this point, I invite Dr. Mahdi onto the stage, or I should call it a virtual stage. Why don't Dr. Mahdi, why don't you please, share your video and your presentation?
Hello, everyone. And thank you very much, Sumit, for introducing me. So today I will talk about CIC IoT-DIAD 2024 dataset, which is a dual function dataset for IT device identification and anomaly detection. As Sumit introduced me, my name is Mahdi, and I'm a postdoctoral fellow at Canadian Institute for Cybersecurity. Today, I will talk about the research objectives and dataset overview, and which contains two different phases. Phase one for device identification, and I will talk about the behavioral-based features for device identification, and I will also talk about identification of the devices based on features from HTTPS and user agent. And in phase two, which is related to anomaly detection, I will explain how we detected individual attack, and then how, as a kind of individual attack detection, and how we, considering all of the attacks in one class, how we can identify, let's say, anomalies among the benign traffic. And I will also talk about a scenario where we had for zero-day attack detection. And at the end, I will talk about the integrated model that we had for both device identification and anomaly detection, and conclusion. So the first objective was IT device identification, how we can identify and classify different type of IoT devices based on behavioral patterns. And also we extracted a behavioral feature from the payload and the header of the packets. And as I mentioned, we have separate features for identifying the IT devices from the HTTPS traffic. And in anomaly detection, we have detection of individual attacks, where we have 7 type of main attack categories, and also detecting anomalies, which we can call it abnormal behaviors against benign traffic. So, and just an illustration of the objectives. So if we are talking about the IoT devices and we want to have a kind of access management system. So initially, when we want to buy something from Amazon, we are logged into our account in Amazon, and then we buy something from Amazon, and then there is a payment that conducted, and in that case, the user is actually doing the whole process. But if you want to replace it with the IoT devices, let's say if an Alexa wanna buy something from Amazon, initially it's received a comment from the user, and then the Alexa should browse Amazon website, and when everything is done and the IoT wanna pay the amount through a payment company, so the payment company should understand that what is the type of the device that is connected and wanna go for a payment, and in that case, let's say that the payment company should understand that it's Alexa and it's a smart speaker and from the Amazon, the vendor's Amazon. And then at the same time, they have to understand the behavior of the device for whether the device is under an attack or the behavior of the device is normal. So in the first phase, we will, as I mentioned, I classify the devices based on the device behavior, and we have different type of IoT devices in Canadian Institute for Cybersecurity devices, camera devices, audio devices, lighting, power outlet, and then home automation and hub devices. And so this is a workflow of the approach that I want to talk for IoT device identification. So first we collected network traffic data from different IoT devices, and then we have a process PCAP to CSV. We extracted features specifically for identifying IoT devices, and then we have some other process for preprocessing and feature extraction, feature conversion, normalization, reduction, and selection. And then when we have a kind of significant features for identifying devices, we used a machine learning model for identifying the type of the device. So as I mentioned, it's a behavioral-based feature for identifying different type of the IoT device categories. And then here we extracted behavioral-based features. I will explain and then put them in some main categories. And we have some specific features for HTTPS and user agent. So if we want to just put them all in some main categories, we have features from network protocol, we have features from handshake and TLS. We have timing feature, and then there are some like very important features from user agent string, user agent browser, operation system, and a device. And also there are some statistical features that we generated based on the previous features that I explained. And the second phase, anomaly detection for IoT devices. So we had some features for device identification. Now we wanna come up with new features to classify the devices and also detect if the device is under an attack. So again, it's similar to the previous framework. We collected traffic from IoT devices, and then in the previous framework, we had some features extracted for classifying IoT devices. But here we need some other features that can help us to detect malicious behaviors from the benign traffic data. So for example, here we want to identify if like a camera is under an attack or a smart speaker is under attack, and how they behave when they have benign traffic, when they are their behavior is normal, or when they have some sort of malicious behavior. So and here we have 7 main attack categories: distributed denial of DDoS, and then web-based attack, Recon attack, DOS attack, and then Mirai attack, and then spoofing and brute force. And for each main attack category, we have some subcategories of those attacks. And if you see in our website, we have main folders for the main attack categories, and inside every folder we have sub-attack categories for different subcategory of the attacks. So, and this is the total number of features that we extracted. The black color are mainly for device identification, and the other remaining features are for anomaly detection. So I just want to explain briefly for the feature that we extracted for anomaly detection. So we have a stream feature, and the definition is a sequence of packet exchange between a specific source and destination. And it actually represents a single communication session between 2 endpoints. And the role of these features in device identification and anomaly detection is identify specific communication session and their characteristics by analyzing stream. And if there is an unexpected spike in traffic or changes in session duration, that can actually signal a potential security incident. And here I just want to compare the actual number that we extracted from the data set. For example, here we have the average of total packet in the same stream in 30 seconds for benign traffic. And then you can see that there is a difference between when we measure it for benign traffic and then when we have it for DDoS attack and also for spoofing. So, and for channel features, the channel is the communication pathway between 2 devices, and is present the logical connection for which data is transmitted. And what is the role of this feature in identification and anomaly detection? It actually helps in mapping out the network tractions, showing which devices are communicating with each other and how frequently. And sudden increase in an unexpected communication path can indicate compromised device or unauthorized data transfer. And again, if you want to compare this feature between the benign traffic and different attack, so we can see that for benign traffic, average of total packet in the same channel for 30 seconds was 234. And we can see that for other attack categories, specifically for DDoS and then Recon, it is specifically for DDoS, it's much higher, and also for Recon attack. And Jitter also is very important feature. It's the variability in packet arrival time. And it's measured the difference in the delay of packets as they travel through the network. And the role of this feature in identification and anomaly detection, it consists jitter pattern help to in identifying the type of traffic, and sudden increases in jitter can indicate network congestion, faulty devices, or deliberate attack aimed to disturbing the communication. And again, if we want to compare the jitter the average sum of jitter of the same stream in 30 seconds. We can see that for DOS attack, it is very less than benign traffic, and also for brute force, it's much higher than benign traffic. And if we want to compare three of them in terms of the numbers for benign traffic and different attack categories, of course, for one individual feature, we may not be able to have a kind of strong difference between the benign, but when we compare and when we have three of them together, then and the combination of these three features can help to identify anomalies against benign traffic. So we also extracted these features in different time period in 1 second, 5 second, 10 second, 30 second, and 60 second. So again, combining all the three features in one time may not help, but if we calculate in different time period and have all of them together and train a machine learning model for identifying anomalies or abnormal behaviors against benign traffic, it is very helpful. So the advantages of having different calculating these features in different time periods is enhancing anomaly detection and comprehensive behavior, and also resilience to noise. And there is a disadvantages because we will have more features, and definitely the data set would be larger. If we want to train a model, the training time would be higher than when we don't have for the different time. But when we have all of the features, we can go for feature extraction, feature selection to come up with some specific features for the task that we want to do for either for anomaly detection or for device identification. So, and we can see that here for 1 second, 5 seconds, and 30 seconds, 60 seconds, the numbers are different for benign traffic and different attack categories. And we also have some new statistical features that we extracted from the data set. So count, mean, variance, and sum. And we have calculated for all the features that we extracted. Again, we can see that count, mean, and variance, there is different between the benign traffic and different attack categories. For example, here we can see that the count is 97 for benign traffic, but for DDoS is much higher. And even for the DOS is just 2.4. And again, for the spoofing attack here is much higher than benign traffic. So this is what we have I just explained for the all the feature together, a stream for different time, and then we extracted different additional statistical feature, count, mean, and where, and then for source IP, and then for channel, and for stream jitter. So totally we extracted 132 features for both device identification and anomaly detection. And now to see the quality of the features that we extracted, so we can see that for different individual attacks against benign, we have calculated accuracy, precision, recall, and F score, and we can see that the performance is very good for each attack. And also we combined all of the attacks in one class, and as a binary classification, we used XGBoost to and other machine learning models to detect that attack categories against benign traffic, and we can see that the XGBoost classifier performed better and then less training time compared to decision to random forest and some other machine learning models. So And we also to see the effectiveness of the feature that we extracted. It is a simple scenario for zero-day attack. So for training, we didn't consider the brute force. Trained the model based on the other attacks and then benign, and then we used brute force in testing. So of course, the result is not as good as the individual attacks, but here, since the model didn't see the patterns of that specific attack, so the performance for example, for Recon attack and web-based attack was less than the others, but still it's more than 90%. So, and this is the integrated model that we had for both device identification and anomaly detection. We have a extracted feature for both phases, and then we classified IoT devices, and then we detected anomalies against the benign samples. So, and we have, of course, two label, MAC address for device classification, and then another label for anomaly detection. So, and this is a result for both phases. So classifying IoT devices and then detecting anomalies against the benign samples. In conclusion, what we have done, we come up with a fast and accurate model that was developed using behavioral-based feature to classify the devices with the minimal computational overhead. We extracted behavioral-based features, and we didn't consider the identity-based features. For example, MAC address, we didn't use MAC address for the identification. And these features were sufficiently and these features were sufficiently effective in classifying the IoT devices. And we also consider a scenario where we have traffic for HTTPS, and those features were useful for identifying the devices. And we extracted a specific feature to identify malicious behavior within the benign traffic. The extracted feature include key characteristics such as stream, channel, and jitter calculated over multiple time period, along with various additional features. And we come up with a unified model, which was built to first identify device type and then detect anomalies, enabling a robust IT security. And thank you very much. If you have any question, I will be happy to answer.
Thank you, Dr. Mahdi, for this insightful presentation. Let me just see. It seems we have a lot of questions, but before we move on to the next speaker, I think we have time to ask you one question. So the question is, did you apply any feature selection techniques to reduce the dimensionality of the feature space?
Yeah, that's a nice question. Yes, because we have many features for anomaly detection and device identification. And of course, we don't need all of them together for specific tasks. If we want to go for device identification, we can use feature selection techniques to reduce the number of features and then use those features. And of course, we have to compare with the total feature, but we have done it. It's available in the paper that we published for this dataset.
Okay. Thank you, Dr. Mahdi. Thank you for the presentation, and thank you for also taking the question.